Hello everyone, and welcome to the Free Fall Post-Lab. Hopefully you've got your completed lab sheet out, right, based on the pivot interactive of the falling balls. Remember that we are studying free fall, which means falling under the influence of gravity only. So gravity is the only force that's acting. Right? No air resistance effects, no when you're throwing it or after you catch it, right? Just gravity. And we can approximate that inside of the video, A, because it's an extremely high-speed video, 1,500 frames per second, right? And because it's over a small distance, and they're fairly small little balls, right, which are round and so aerodynamic. So even though they weren't really in a vacuum where there's no air resistance, it's pretty close, okay, at least over those small distances. So, first question I want to answer here is, was the acceleration of your freely falling object uniform? Right? Meaning, was it constant? In other words, was it like the motion of a cart going up and down a hill, right? Which we've seen as uniformly accelerated motion. We did a whole unit, if you remember, on uniformly accelerated motion. So is this really just another example of that? Well, let's look what you got. Hey, you made a graph of velocity in meters per second versus time in seconds for the ball, and didn't your graph look something like that? A nice linear graph going through 0, 0. And now, it took you a little while to get there, right? You had to do several steps, but you got to that velocity time graph. Now, let's talk about the slope of this graph. Since this is a graph of velocity versus time, what does this slope represent? Well, it represents the acceleration. Looking at the slope of your graph, was it a positive or a negative slope? Since it's sloping down, that makes it a negative slope. And can you tell whether your slope, not the graph, but your slope, is increasing, decreasing, or is your slope constant? Look at your graph. It's a linear graph. Right? What's special about the slopes of linear graphs? They are constant. So by looking at your velocity time graph, we can determine that the acceleration is negative and constant. And although I just had you sketch this graph, right? I didn't have you make it inside of graphical analysis or anything, right? You can hopefully surmise that since your acceleration is negative and constant, on a graph of acceleration in meters per second squared versus time in seconds, a negative constant acceleration would look like this. Notice it's negative, it's underneath the time axis. Right? Time axis is up here. And it's constant because it's a horizontal line. Isn't that what the graph of a constant looks like? Any time you choose, you get the exact same acceleration. So these are graphs of uniformly accelerated motion, but specifically for free fall near the surface of the Earth. So the next question I want to answer is, now that we know that it's uniformly accelerated motion, was there a particular uniform acceleration, right, that we could use? Well, let's go to the data. So you'll see a bunch of different data points here. Let's look at the first column. Free fall acceleration near the surface of the Earth. Now look at all these values. You'll notice that they're all negative, right? And they all are fairly close to one another, within about a tenth or so either way. Right? On average, to 2 sig figs, it works out to be negative 9.8. 2 sig figs here seems reasonable because everybody's got a 9 for the first digit, and the second digit is where we start to get some 7s, some 8s, some 9s. But if we take the average, it looks like it's a negative 9.8. 9.8? Isn't that a number we have seen before? So a little less than 10. Negative 9.8 seems to be what we get. Now this value is so very important, the acceleration of a freely falling object near the surface of the Earth, that it is given its very own symbol, right, and its very own name. And that is little g. So little g here is negative 9.8 meters per second squared. This is the acceleration due to gravity near the surface of the Earth, or shorthand is free fall acceleration. Okay, acceleration due to gravity near the surface of the Earth. Now, hopefully you're saying to yourself, we had a 9.8 number before, and we also called that little g. Don't worry, this will come up. Why we've seen it before. Just give me a minute here. Right? But this is our experimental value that we saw. In fact, this is pretty much what everybody got, right? I mean, within about 1% or so above or beyond, and on average, this is exactly what we got. Right? So this is the acceleration due to gravity. And be careful, this is near the surface of the Earth. I am not guaranteeing that if you did this same experiment on the moon, that you would get the same result. Right? Only that if you do it near the surface of the Earth, that you should get this result to a couple of sig figs, give or take a little bit. Now, what does this mean? Well, if we write a for every statement, it's a little hard to interpret with these units. Right? It might be a little easier to interpret if we go back to the units of the slope here. Right? That's what it is, after all. That's how you found it in the lab, was the slope of your velocity time graph. Well, look, a slope here would have rise over run. The rise would be in units of meters per second. The run would be in seconds. Now, yeah, a meter per second reduces down to a meter per second squared. Right? But helps to have them in the meter per second every second thing if we're going to do a for every statement. So keeping that in mind, it tells us that for every 1 second your ball fell, its velocity increased by 9.8 meters per second. It got 9.8 meters per second faster every second. Notice that doesn't tell you how fast it's going. It's telling you how fast it gets faster. This is an acceleration, the rate of change of velocity. Now, why is it negative? Well, experimentally, it's negative because the object was going downward and speeding up. So when an object is going down and speeding up, right, the acceleration has to point in the same direction it's moving, which is down, which is negative. Exactly what we saw experimentally. Right, so the negative acceleration here is because it has negative velocities, it's falling down and it's speeding up. Same rule we found, right? When they point in the same direction, you're speeding up. When the direction you're moving and the acceleration point in opposite directions, you're slowing down. In this case, you're speeding up, right? So negative. Now, the other thing we could do in the lab was we could compare different mass balls to see what effect that had on this. So, again, let's go back and look at our data again. And let's this time compare the free fall accelerations near the surface of the Earth to the masses. Now, you'll notice again, these are pretty much the same thing, right, every time. But look at the masses. The masses went anywhere from a low of 8.6 to a high of 535.1 grams. Right? This is what? 50, 60 times as big. 50 times as big, right, as this. And it still gave you the exact same value. Sure, this one, 535, was 9.7. But, you know, this one was 9.8, and this one was 9.8, and it averaged out to 9.8. In other words, you know, we are at a big multiple here of a big range of masses, right? And yet they all seem to have the same acceleration. Interesting, isn't it? Okay. So if we were to have graphed acceleration versus mass, since it doesn't seem that the mass has any effect, wouldn't that have been a horizontal line at negative 9.8? Right? You get the same acceleration regardless of mass. And it's pretty convincing because it's, you know, many, many times the smallest mass to the biggest mass, 8.6 to 535. That's a big difference, right? Many multiples. So it appears that the mass doesn't affect the acceleration. Now, we have to be careful here, though, because you might be saying, wait a minute. Do you mean if I drop a bowling ball and a feather that they're going to fall with the same acceleration? No, that's not what we said. We said that's only true if we can neglect air resistance if these objects are in free fall. This was first discovered by our old friend Galileo Galilei and is often known as Galileo's Law of Falling Bodies. In a vacuum, all objects fall with the same uniform, meaning constant, acceleration regardless of mass. So as exactly what we found in the lab. Now, there is no actual proof that Galileo ever dropped objects. And he would have obviously had a hard time timing them. They didn't have clocks back then. He was the first one to do a lot of the work with pendulums, and so they didn't even have pendulum clocks, or they were just being developed. So he wouldn't have been able to time anything, and he certainly wouldn't have been able to make a 500 frame per or 1500 frame per second video like we used, right, to analyze this. So there's no actual evidence. There are some apocryphal stories that perhaps he went up onto the Leaning Tower of Pisa and dropped objects off of the tower to see when they'd land, but he never wrote about it. He didn't write about it in any of his books or letters or anything to say that he'd actually done the experiment. Right? But this is something he surmised. He actually wrote in one of his books a what's called a proof by contradiction, a little thought experiment that explained why objects falling in a vacuum should fall at the same rate. But remember, Galileo was a great one for thinking about what happened to objects, what happened to the motion of objects, if you could get rid of the resistance effects. Remember his idea of inertia that said if we didn't have any friction, right, once you got an object going, it should just keep going forever, right, with the same velocity. There's nothing to resist its motion. Objects in motion tend to stay in motion. Well, he did the same kind of thing here. He tried to imagine what would happen. Okay? Now, real cool little demo here. So it's a classic. It's called the feather and penny demo, okay, where we drop a feather and a penny in a vacuum. Okay? Now, if you're in class, you're going to see this, and it's really cool to watch in real life. Okay? But I also have a video. This is actually part of a Mechanical Universe video, and it's showing you a very high-tech feather and penny experiment. So watch this little video.
What happens if a penny and feather drop simultaneously from the same height? They behave exactly as we'd expect, each falling at a very different rate than the other.
That's in air.
But that's only because of the effect of air resistance on the two objects. In a vacuum, a penny, a feather, and any other object will fall at exactly the same rate. With virtually no air remaining inside the glass tube, the penny and feather are now in a vacuum. When the penny and feather are released, we'll witness the law of falling bodies in action. Without the effect of air resistance, in other words, in a vacuum, all bodies, regardless of their weight, will fall at exactly the same rate.
See how they fall right next to one another? Only in a vacuum.
When Apollo 15 astronaut David Scott explored the airless surface of the moon, he couldn't resist repeating this classic experiment for all the world to see.
Well, in my left hand I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
Now, one thing, did you notice how slow, right, that feather moved? Feather and hammer here in the video? Let me show it to you again, all right? That's just that last little part, and I want you to watch how slow they fall.
Same time. How about that? Mr. Galileo was correct in his findings.
So if we were to measure that acceleration, right, we wouldn't find a negative 9.8 meters per second squared like we did on Earth. And so that number is very important because we live on Earth, but remember that it can be different at different places. And eventually we'll do a little unit on what's called universal gravitation, at which point we'll be able to discuss a little more why the acceleration due to gravity might be different on the moon than it is here on Earth. Okay, but for now, we don't have quite enough physics.
Discovered something very unusual at that museum. Oh my God, what? Well, if you drop a feather and a bowling ball in a vacuum, they'll fall at the same rate. You think you've seen it all in this job, and then something like that comes along.
Ah, The Simpsons. So, why? Why do all objects fall at the same rate in a vacuum? Right? The same uniform acceleration. Well, let's do a little Newton's laws analysis here. Here is our freely falling object. What forces act on that ball as it falls? Of course, gravity acting down. Anything else? Not if it's free fall. Remember, by definition, free fall, the only force is gravity. No air resistance, nobody touching it, right? Just gravity. Now, because gravity is the only thing that's falling on it, acting on it, there is a net force. And as we know from Newton's second law, net forces result in accelerations. Net force is mass times acceleration. So in this case, the only force is gravity, which acts down, which makes it negative. Notice I put the negative here and I took the arrow off, so it's negative. And we know that near the surface of the Earth, we can calculate the force of gravity acting on an object, otherwise known as its weight, using mass times gravitational field strength. Now in this case, this little g is the gravitational field strength, right? Because we're using it inside of f of g as mg. So we have negative mg equals ma. Anybody see what happens next? Anybody? You see what that implies?
Now remember, Newton realized that Aristotle was wrong and force was not necessary to maintain motion. So let's plug in our 9.8 meters per second squared as A, and we get force, Earth gravity, equals mass times 9.8 meters per second. So we can see that ma equals mg, and what do we know from this?
We know that Newton was a really smart cookie. Oh, is that where Fig Newtons come from?
No, Fig Newtons are named after a small town in Massachusetts. But don't write that down. Now, if ma equals mg, what does that imply?
I don't know.
Wait, but how can you not know? I just told you. Have you suffered a recent blow to the head?
Hey, you don't have to be so mean.
I'm sorry. Have you suffered a recent blow to the head?
No, you just suck at teaching.
Really? Of those two explanations, which one seems the most likely?
Sheldon, I'm trying to understand, but you're going too fast. Can you just back up a little bit?
All right. It's a warm summer evening in ancient Greece.
Not that far back.
Okay. At what point did you begin to feel lost?
I don't know. Where were we looking up at the night sky?
Greece.
Damn it!
Look, there's no need to get frustrated. People learn at different rates. Unlike objects falling in a vacuum, which... ma equals mg...
Squared?
No.
Aristotle?
No.
5?
love that clip. You see where he's trying to teach her the exact thing we are learning right now? So what does this show? Well, hopefully some of you are looking out there and saying, wait, there's mass on this side, there's mass on this side, so what happens to those masses? They cancel out. And if there's no mass in the equation, that means it doesn't affect the acceleration. That's math, though. We need to be a little careful here. This is actually a super deep thing. Okay, a very deep thing in physics that these masses cancel out. Because whether you realize it or not, these are two different kinds of mass. The mass over here in the MA is what's known as inertial mass. It's a measure of the inertia of the object. If you wanted to measure something's inertial mass, you would apply a force, measure the acceleration, and then you could calculate the mass. Right? So we could do a lab like that, right? We could do a modified Atwood's machine, measure know how much force we were applying, measure the acceleration, and figure out what the mass is. That would be the cart's inertial mass. Okay? But the M in the mg is what's known as gravitational mass. This is not measuring the mass directly, but rather inferring how much mass there is by figuring out how much the object weighs, how much the force of gravity is acting on it. So if we took that cart and we put it on a scale, right, the scale might read its mass, but really what the scale is doing is measuring, how much does that cart weigh, and then converting over to mass, because it knows g inside of it. So this is gravitational mass. Okay? Now, in Newtonian mechanics, which is what we study, there is absolutely no theoretical reason why an object's gravitational mass and its inertial mass should be equal to one another. Yet, if you do those kinds of experiments, measure how much mass something has by using F equals ma, the inertial part of it, measure how much mass something has by measuring its weight and converting, right, the gravitational mass, we will find that those things are always equal to one another. And they have done experiments that go way out in decimal places, and still they get the exact same mass. In fact, this is such a deep idea that it's one of the basic postulates of Einstein's general relativity. General relativity is that whole curved space-time, black holes, all that kind of stuff. Okay, and one of the basic postulates is that this is actually true. That gravitational mass and inertial mass are the same thing. So it's a very deep idea. For us, we're just going to cancel it out. But look at the equation again. Right? If something had twice the mass, that would mean that there would be twice as much gravity acting on it, right? And if there was more gravity, that would tend to want to accelerate it faster. But there would also be twice as much inertia, twice as much resistance to changes in its motion, and those two things cancel out. You put them in a ratio, right? Mathematically, they cancel out. More mass means more gravity, but more mass also means the same amount of more inertia. Right? So those two things cancel out. I know, that is a really, really deep idea. Right? And while Sheldon understood it, couldn't really explain it very well, and Penny was just lost. But hopefully you're not. This will come up, though. We will discuss this more. But if we cancel the masses out, then notice the acceleration it has is just equal to negative g. There's no time in here at all, right? There's no t's. That means it's a constant. So our physics is saying, if the weight is constant, which it is near the surface of the Earth, right, then the resulting acceleration will be constant or uniform. And it'll be equal to negative g. And we, of course, know what the gravitational field strength is near the surface of the Earth. It's negative 9.8 newtons per kilogram. But wait a minute, you might be saying. Those aren't acceleration units. Those are gravitational field strength units, which means that for every kilogram of mass, there's an additional 9.8 newtons of force of gravity or weight. Right? Every 1 kilogram of mass, the gravitational field applies an additional 9.8 newtons of force. That's not acceleration. Oh, but let's remember something here. The newton is a derived unit. It comes right from this equation. 1 Newton of force is the force required to make a 1 kilogram object accelerate at 1 meter per second squared. A Newton is, in fact, a kilogram meter per second squared. And so the kilograms cancel, and we are left with meters per second squared. So in fact, a Newton per kilogram is equivalent to a meter per second squared. So this is actually, the acceleration is the gravitational field strength, which is negative 9.8 newtons per kilogram, which is the free fall acceleration of negative 9.8 meters per second squared. Why then 2 sets of units? Because they mean something different, right? And we should be specific in that. You will see me doing this in my PowerPoints and keys and things like that. If we're using f of g as mg, you'll see my little g written as newtons per kilogram, because that's what we're talking about. How much force is applied for every kilogram of mass. However, if I'm doing some sort of motion equation, then we might be relating it to the acceleration, in which case I will use negative 9.8 meters per second squared, which means the velocity changes 9.8 meters per second for every second that goes by. All right, so it's important that your units here are contextual. It's all context. Are you talking about gravitational field strength, or are you talking about the acceleration? So this little proof will come back up again for us in a different unit, but this is the little physics proof here that explains why our acceleration ended up being the same number as our gravitational field strength, negative 9.8. It also shows why the mass doesn't really affect it. Galileo didn't know Newton's second law, so he couldn't explain this, right? He just surmised that it would be experimentally true. But again, it's a rather deep idea, because gravitational mass and inertial mass, while fundamentally different things, are always equivalent to one another. Right? More mass means more gravity, but more mass also means proportionally the same amount more of inertia. Right? Gravity would make it, more gravity would make it accelerate faster, but more inertia means it's more resistance to changes in its motion, right? Would lower the acceleration. So that little ratio, the masses cancel. Now, a couple of things. So in this lab, we only did falling straight down. We're going to actually go back and revisit that video and do on the way up and at the top and everything else. But just briefly here, what would the force diagram look like for a ball on its way up? After it leaves your hand, right? After it leaves your hand, otherwise it wouldn't be free fall, right? But after it leaves your hand, what would the force diagram look like? Wouldn't it look just like this? Right? The only force acting on it on the way up, after you throw it, right, is gravity. And if gravity's the only force acting on it on the way up, shouldn't the acceleration be the same thing? Ooh. What about at the very highest point? Right, that top point in the video? Well, again, what forces act on it? Just gravity. So is it accelerating at that top point? Yeah, this much. Because the only force acting on it is gravity the entire time if it's in free fall. Now, I call that complete motion projectile motion. The concept builder guy tends to call the whole thing free fall, but I kind of like projectile motion more for that one. I call free fall when it's falling, so down, right? Some people tend to call that kind of two different things, but, you know, I'll use my language. You might see it a little different in the concept builders. Now, since we have just shown and proven experimentally and theoretically for that matter that free fall is uniformly accelerated motion, all of the things we've learned about uniformly accelerated motion will apply to free fall, including our old friends, the kinematic equations. You remember those 4 guys, right? Well, here they are. At least these are the free fall versions. Now, hopefully these look familiar to you. I have done a couple of things, though, to convert them to free fall versions. Anybody see what I've done? A couple of things. First thing, notice where normally I had written X's, I've now written Y's. Well, why would I do that? Well, recognize that the x minus x sub o was the displacement, right? The change in position of the object. So a y minus y sub o is still displacement, but y's are vertical. Right? So I replace the x's with y's because we're talking about a vertical motion here. I also put some subscripts on of y's to turn the velocities into vertical. But note the other thing I did. Instead of writing an a for an acceleration, I plugged in little g. Because that's what it is if we're near the surface of the Earth, right? That's something that we now know. It's a given. We can use it. I don't have to tell you every time. As long as the problem, you can assume that we're near the surface of the Earth, you can use negative 9.8 meters per second squared for the acceleration and plug it into the problem. Now you have to be a little careful. The negative is because it is accelerating downward, because the net force is downward, gravity, right? So down has to be negative if you're going to use this negative. Conventional coordinate system, up is positive, down is negative. So there's a lot of negatives in these kinematic equations when we get around to practicing them. Right? And we will do a few problems with them as well.